Hey there, Mr. H here. Today I want to talk about Kirchhoff's rules. Kirchhoff's rules give us a way to talk about current and voltage at any point in our circuit, and so it's a very powerful set of tools that we can use when we're doing physics. Let's start by talking about Kirchhoff's loop rule. So Kirchhoff's loop rule states that the sum of all potential differences around any closed loop of a circuit will equal 0. And there's one subtlety here, and that's any closed loop of a circuit. What do I mean any closed loop? Well, I could draw multiple closed loops around this circuit. I could draw this closed loop. By closed, I just mean I come back to the same point that I started at. There's a closed loop. Here's a closed loop, right? I could just skip this branch and go over here. And from these two loops, it's tempting to say that closed loops are where current flows in a closed loop, but not necessarily, because we can draw a third loop and Kirchhoff's rules will still apply. Draw a third loop here. So here are the three loops that I want to analyze really quickly. Okay, so first let's talk about loop 1. Loop 1. And in order to talk about this, let's write our loop rule in sort of math language. So what it says is the sum of all potential differences around a closed loop of a circuit will equal 0. So in loop 1, the potential differences will be here, here, and here. Okay. So when we encounter a resistor and we're moving, let's define a direction. Let's say we're going around this way. Okay, let's say we're going around the loop clockwise. When we are going clockwise and the current is also going clockwise, so we're sort of analyzing in the same direction of our current, we're tracking along in the same direction as our current, and we encounter a resistor, we say there's a voltage drop. Okay, and so there will be a voltage drop of, well, we don't really know, but let's call it delta V1. So we'll have a voltage drop minus of delta V1. Okay, let's continue on. We're tracking along, and we encounter another resistor. And we're tracking in the same direction as our current, and so another voltage drop, delta V2, we'll call it. And we keep going, then we get to a voltage source. And the voltage source, when we encounter a voltage source and we enter the negative terminal, we're going to treat that as a positive contribution to our loop rule. So delta V, we just called it V. Okay, so if I were to be analyzing, let's say instead I wanted to go counterclockwise. If I wanted to go counterclockwise, then I would say, okay, well then I'm going in this direction. I go around. This is opposite the direction of my current, and so I would get positive. Let's do it this way. I'd get positive delta V2. Then I would encounter this resistor. I would get a positive contribution from delta V1, and then I would encounter this guy. So I would get I'm entering the positive terminal, so I would get negative delta V. And we see that these are basically the same. We just kind of switched. This is like picking a coordinate system in a dynamics problem or a kinematics problem. Okay, so we just arbitrarily select clockwise or counterclockwise to do our analysis, and that's where the minus or positive signs come from. Okay, but in either case, in fact, let's get rid of all this. Let's just do the case where we go clockwise for all of these. We'd get the sum of those voltages, or the sum of those potential differences will equal 0. Okay, very good. And then we could apply Ohm's law to each of these, start talking about current if we really wanted to. We don't want to. Okay, loop 2. Let's do a second loop. Well, we're good at this now, so we encounter the first resistor. We get a voltage drop because it's in the direction of our current, so delta V1. We encounter R3. Delta V3, and again it's negative because we're going in the direction of our current. And then we encounter the negative terminal of a battery, so we get a voltage gain. Plus delta V equals 0. And that's great. From this, we could, if we needed to, infer that delta V2 and delta V3 are equal to each other, right? We could do that because these two components of the equation are the same, and so these two must be the same if we get the same result here. Alright. But we're not going to do that. We're just going to set up a third loop. We're going to set up a third loop, and this one is a little bit more subtle. So let's go clockwise again. We're going clockwise around this loop. Here we're going in the direction of the current when we encounter R3, so we get a voltage drop, delta V3. I guess I should label this, be consistent. Loop 3. I have delta V3, and then here I'm fighting the current. I'm going upstream. The current is going opposite the direction of my analysis, and so I actually get a voltage gain. That's the convention. I give it a voltage gain, delta V2. And those are equal to 0. Now, what do I see? I could take this a step further and say delta V2 equals delta V3. And in fact, for any parallel branch of a circuit, I'll get this same behavior. I'll do a closed loop around it, and I'll see that the voltages, or the potential differences, are equal. And so this is where that general rule that we're so used to applying of the voltage drops across branches of a parallel section of a circuit are equal to each other. This is where that behavior comes from. It's from Kirchhoff's loop rule. Okay, so if you're ever on your AP exam and you need to explain why the voltage drops across branches of a parallel section are equal to each other, you cite Kirchhoff's loop rule. And Kirchhoff's loop rule is also a statement of conservation of energy. It says that we give the circuit that much energy to start, and so it can only lose, and in fact it has to lose that much energy by the time it gets around a closed loop. Okay, so conservation of energy. Woohoo! Alright, now let's talk about the other rule that Kirchhoff has for us. Kirchhoff's junction rule. So Kirchhoff's junction rule states, I gotta get all of it there, gotta make sure. Kirchhoff's junction rule states that the sum of the incoming current will equal the sum of the outgoing current at any junction in the circuit. So let's write that again in kind of math language. So the sum of the incoming current, I guess I'll call it I incoming, equals the sum of the outgoing current at any junction. And we say at any junction, but the reality is, well, I'm going to add a little period here. The reality is that we don't even have to pick a junction. We do not even have to pick a junction. So let's see if I can erase our loops since we're done with our loop rule. Okay, and let's start looking at some junctions. Let's do junction A. Let's do junction B. And then just for fun, let's do not a junction C. And it seems a little trivial, but it'll tell us something important. Okay, so at junction A, I guess I should pick blue. At junction A, we see that there's some current incoming here. We'll call that I1. And we also see that there's some current outgoing here. We'll call that I2. And there's some current outgoing here, I3. All right. And so our junction rule says that all incoming current, which is just I1, has to equal the sum of all outgoing current, which is I2 and I3. Okay, that wasn't so bad. Now let's do junction B. Junction B says we have some incoming current, I3. We have some incoming current, I2. We have some outgoing current. We'll call it I4, but we'll learn something about it in a second. I4, and we see that the incoming currents, I1, or I2 rather, and I3, have to equal the outgoing currents, which in this case is just I4. And what do we see? We see that I1 and I4 are the same thing. Okay, they're the same thing, so I1. Okay, and then let's look at our seemingly trivial case where we have some incoming current. We'll keep calling it I4. We have some outgoing current, and as you may expect, I'm going to call this I1. And we say that, okay, I1, well, I4 we say is incoming, equals I1. Whoa, spooky stuff. Okay, so the junction rule is really what tells us that along series branches of circuits, the current should always be the same because we can draw a junction at any point along this series component of the circuit, and at those junctions the incoming current has to equal the outgoing current, even if that junction has a resistor on it, or even if that junction has a voltage source on it. It doesn't matter. At every single junction, the incoming must equal the outgoing. And so this is our explanation for why the current along series branches is equal but divided at parallel branches. Okay, so Kirchhoff's rules are actually very powerful explanatory tools. Okay, and this is a statement of conservation of charge. Conservation of charge. Because remember that charge is equal to, or current rather, current, you have this equation on your formula sheet, is equal to some amount of charge. Current is equal to some amount of charge over some amount of time. In fact, there might even be a delta up here, I'm not sure. But some amount of charge over some amount of time. And so we say that charge is conserved because all of that charge has to flow through this point. None of that charge can get lost as it flows through any particular junction. Okay, so this is a statement of conservation of charge. And what we'll usually do with these rules is use them together. We will use a system of equations that has a bunch of loops and a bunch of junctions. We'll use Ohm's law to convert these into IRs, IR, 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 and then we'll substitute in these expressions for I. We'll have a ridiculous number of variables, but we'll also have a ridiculous number of equations to solve for those variables. Okay, well that's all I have for this time. See you next time.